When we step outside on a clear night and look up at the star-dusted canopy of heaven, we are met with a comforting illusion. We see a definitive landscape, stars pinned against the dark, distant galaxies glowing like fragile embers, and a stillness that suggests an end. For the vast majority of human existence, our ancestors naturally assumed that what we could see was all that existed. We built our mythologies, our philosophies, and eventually our sciences around this visible architecture. But the cosmos holds a fundamental truth that shatters this geocentric complacency. Our view of the universe is severely, artificially restricted. It is a masterpiece veiled in darkness, concealed from our eyes by its own finite age and the unchanging speed limit of light. Every telescope we build, from the simplest optical lenses to the most advanced space observatories, operates within a strict cosmic boundary. Because the universe is approximately 13.8 billion years old, light from the most distant structures has only had that exact amount of time to travel across space to reach our planet. This limitation creates an absolute bubble around us, the observable universe. But space itself is not static. It has been stretching and expanding for eons. Because of this cosmic tide, the farthest objects, whose ancient light is just reaching us today, have been cast much farther away. Today, they lie at a proper distance of roughly 46 billion light-years in every direction. This means our observable bubble spans a staggering 93 billion light-years in diameter, packed with an estimated 2 trillion galaxies. But what happens when we reach that edge? What lies in the uncharted dark beyond the cosmic light horizon? To understand the true scale of what lies beyond, we must first confront a deceptively simple question that puzzled the greatest minds of the 19th century. Why is the sky dark at night? The immediate, intuitive answer is that the sun has set, leaving our side of the Earth in shadow. But on a grander cosmic level, this answer is incomplete. If the universe were infinite in extent, and if it had existed forever in a static state, then no matter which direction you pointed your eyes in the night sky, your line of sight would eventually land on the surface of a star. The night sky should not be dark. It should be a solid, blinding sheet of starlight, as bright as the face of the sun itself. This intellectual emergency is known as Olbers Paradox, named after the German astronomer Heinrich Wilhelm Olbers. The solution to this paradox is the very key that unlocks the nature of the unobservable universe. The sky is dark for 2 reasons. First, the universe is not eternal. It had a definitive beginning 13.8 billion years ago. Stars have not been shining forever, meaning the light from the most distant ones simply hasn't had enough time to reach us. Second, the universe is expanding. As light travels across expanding space from deep cosmic depths, its wavelength is stretched and elongated. This process, known as cosmological redshift, shifts visible starlight down into the invisible infrared and microwave spectrums. The darkness of our night sky is actually a silent testimony to a dynamic, expanding cosmos, and a warning that the most critical components of our universe are completely hidden from our biology. If we wish to map the invisible reality beyond our horizon, we must inspect the most ancient boundary available to human instruments, the cosmic microwave background, or the CMB. This omnipresent glow is the holy grail of modern cosmology. It is a pristine snapshot, an ancient screenshot of the entire observable universe, captured when it was only 379,000 years old. Before this moment, the universe was so hot and dense that it existed as a blinding, opaque plasma of electrons and protons, trapping light in an endless cycle of scattering. But as the cosmos expanded, it supercooled to a critical threshold, allowing stable atoms to form. In an instant, space became transparent, and the first photons were unleashed across the void. This ancient light has been traveling through space for nearly 14 billion years, cooling down to a freezing 2.725 Kelvin above absolute zero. When we look at the CMB map generated by ESA's Planck satellite, we see that it is strikingly beautifully uniform. The temperature across the entire sky varies by only a fraction of a degree. However, within that uniformity lie microscopic fluctuations, subtle ripples in the density of the early primordial soup. These tiny variations are not random noise. They are the seeds of every galaxy, every star, and every planet that would ever form. And more importantly, they are a mathematical code that reveals the hidden properties of the space that lies far beyond our optical sightlines. The remarkable uniformity of the cosmic microwave background allows scientists to deploy one of the most powerful concepts in astrophysics, the cosmological principle. This principle dictates two fundamental rules for our universe on the largest cosmic scales. It is homogeneous, meaning it looks the same no matter where you are standing, and it is isotropic, meaning it looks the same no matter which direction you choose to look. There is no special place in the cosmos. There is no center, and there is no preferred orientation. When we apply the cosmological principle to the mystery of what lies beyond the cosmic light horizon, the initial answer is quite straightforward. If you were to teleport to a galaxy situated at the very edge of our observable bubble, your new viewpoint would look entirely familiar. You would not find yourself looking at an empty abyss or a sci-fi barrier. Instead, you would find yourself at the center of your own new observable bubble, surrounded by an identical network of galaxy clusters, massive voids, and cosmic filaments. Lying beyond the horizon, quite simply, is more of the same. The cosmic web branches out for hundreds of billions of light years past our view, populated by mature, chemically evolved galaxies that we will never directly see. But this realization triggers an even deeper question. How far does this pattern extend? How much universe is actually out there? Answering the question of how much universe exists requires us to determine the global shape and curvature of spacetime. Albert Einstein's monumental theory of general relativity taught us that space is not an empty, passive stage. It is a dynamic fabric that can be bent, stretched, and warped by the presence of mass and energy. The total amount of matter and dark energy in the cosmos dictates its eventual fate and its overall geometric structure. This relationship is quantified by the density parameter, represented by the Greek letter omega. If the self-gravitation of the cosmic web is immense, it will warp space inward, closing the universe into a finite, boundaryless sphere where omega is greater than 1. In this closed universe, parallel lines of light will eventually converge. If the universe is dominated by an open-ended, repulsive vacuum force, space forms a negative, saddle-like shape where omega is less than 1, causing light to diverge. But if the forces are perfectly poised on a cosmic knife edge, the global geometry is completely flat, and omega equals exactly 1. To solve this mystery, cosmologists turned to cosmic geometry, using the ancient rules of triangles mapped onto the oldest structures of the sky. By analyzing the precise angular separation between the hotspots on the cosmic microwave background, scientists built a giant cosmic surveyor's wheel. In a spherical universe, the interior angles of a giant triangle would sum to more than 180 degrees. In a saddle universe, they would sum to less than 180. But when the data from the Planck satellite was processed, the result was undeniable. The interior angles of our cosmic triangles add up to exactly 180 degrees, within a margin of error of less than 1%. Our universe is globally flat. This finding introduced one of the deepest crises in modern astrophysics, the flatness problem. For the universe to be even remotely flat today, 13.8 billion years after the Big Bang, it had to be impeccably, miraculously close to the critical density at the moment of its birth. If the density of the early universe had been altered by even 1 part in a quadrillion, the disparity would have been aggressively magnified over cosmic time. A slightly denser universe would have collapsed back into a fiery big crunch within a few million years. A slightly less dense universe would have flown apart so quickly that galaxies and stars could never have formed. Why was our universe born balancing perfectly on this impossible mathematical knife edge? To solve the flatness problem without relying on pure cosmic coincidence, scientists look toward the field of topology. A universe can be locally flat, but globally closed and finite if it possesses a complex, multi-connected topology. The most famous model of this kind is the 3 torus universe, commonly referred to as the donut universe. First modeled extensively by Soviet physicists Yakov Zeldovich and Alexei Starobinsky in 1984, this concept suggests that space behaves exactly like a classic game of Pac-Man. In a 3 torus universe, Euclidean geometry applies on all local scales. Light travels in straight, parallel lines, and triangles always add up to 180 degrees. Yet, the volume of space is completely finite. If you fly your spaceship in a straight line for long enough, you will never encounter a physical boundary. Instead, you will simply return to your point of origin from the opposite direction. If our observable bubble were larger than the boundaries of this torus, we would experience a cosmic hall of mirrors. We could point our telescopes at opposite sides of the sky and see the exact same galaxy at 2 different stages of its life cycle. While recent CMB data has found no repeating patterns to confirm a small torus, the intoxicating possibility remains that our universe is a closed, multi-connected hallway much larger than our current view. The leading explanation for our universe's flatness does not rely on complex topologies, but on a mind-boggling event that occurred at the absolute dawn of time: cosmic inflation. Developed by MIT physicist Alan Guth in 1981, this theory suggests that a fraction of a second after the Big Bang, at approximately 10 to the negative 36th seconds, the universe experienced a violent, exponential expansion. Driven by a high-energy quantum field, a patch of space smaller than a subatomic particle ballooned in size by a factor of at least 10 to the 26th in less than a trillionth of a trillionth of a trillionth of a second. This super-luminal expansion acted as a cosmic iron, instantly stretching and smoothing out any primordial curvature, wrinkles, or defects in the fabric of spacetime. Inflation expanded the global universe to such a gargantuan scale that our entire 93 billion light-year observable bubble is just a microscopic speck on a much larger cosmic canvas. Just as the surface of the Earth feels completely flat to a person standing in an open field because the true horizon is vast, our 3-dimensional space looks flat because the global universe is unimaginably huge. Estimates suggest that the true universe outside our view has a proper diameter exceeding 20 trillion light-years, holding millions of times the volume of everything we can ever see. If cosmic inflation is correct, it introduces a terrifyingly beautiful existential reality. If inflation created an infinite, flat canvas of space, then our universe contains an infinite amount of matter and energy. However, according to the laws of quantum mechanics, a finite number of fundamental particles can only be arranged in a finite number of ways within any given volume of space. When you have a finite number of particle configurations operating inside a truly infinite expanse, absolute repetition becomes a mathematical certainty. This means that past a distance of meters, a distance so vast that the number cannot be written down on paper, there is an exact replica of our solar system. There is an identical Earth, an identical room, and an exact copy of you watching this very video. Every life you didn't lead, every choice you didn't make is playing out somewhere across the infinite landscape. But the laws of physics have separated us from our twins. Because dark energy is accelerating the expansion of space, these infinite domains are moving away from us faster than the speed of light, ensuring that our local bubble remains completely isolated from the rest of eternity. As we look out from our tiny island in the deep dark, we must accept that our view of the universe will never get any better than it is right now. We live in a golden age of cosmology. Every single second, 60,000 stars are carried past our cosmic event horizon by the accelerating expansion of space, entering the unobservable zone forever. In 100 billion years, every neighboring galaxy outside our local group will be swept out of view. In 2 trillion years, the cosmic microwave background will be stretched into invisibility, and the sky will be entirely dark. Future civilizations evolving on Earth trillions of years from now will point their telescopes into the void and find nothing but silence. They will never discover the Big Bang. They will never see distant galaxies, and they will believe their home galaxy is all that has ever existed. We are profoundly fortunate to look out at a sky that still remembers its origins. The universe beyond the horizon may be an infinite canvas of duplicates and unseeable wonders, but our local bubble is more than enough to fill us with absolute awe. Thank you for traveling with us to the edge of reality on Science Odyssey. Keep looking up and stay curious.